What's up everyone, Michael here. Today I've got a great video for you guys. We're going to be building a roulette wheel smart contract. A roulette wheel smart contract is actually the first smart contract that I ever built and deployed on Ethereum. To do it, we're going to be using Remix as our in-browser IDE, and we're also going to be using Chainlink VRF. Chainlink VRF is an awesome tool that provides verified randomness on the blockchain. Because your smart contract code is public, if you try and create randomness using some semi-random way, like taking a hash of the current block, hackers can actually predict this and then gamble only when they know what the right answer will be. And you don't want that, because then you'll lose all of your money in your roulette wheel. Chainlink VRF fixes this by providing verified randomness on the blockchain. In this video, first we're going to get set up by installing Metamask and getting some Kovan testnet, ETH, and Link into our Metamask wallet. Then we're going to code our smart contract in Remix and test it. Finally, we're going to deploy our smart contract onto the Kovan test network. The deployed version of the contract would be functioning completely. And if you want to, you could actually deploy it onto the Ethereum mainnet and run your own blockchain casino. Although I don't recommend that because it's probably illegal where you live. All right, let's get started by installing Metamask. All right, well, the first step is to go to Google and search for the Metamask browser extension. The first result will be this Metamask Chrome extension. So go ahead and go to the Chrome store and download it for Chrome. I already have Metamask installed, so I'm not going to download it. But if you are downloading it for the first time, you might want to restart your Chrome browser in order for it to work. Then you can go and pin the extension up into your toolbar. If you're using Metamask for the first time, go ahead and create an account. Once you have an account, go ahead and open Metamask. And then you'll see your account here and your current ETH balance, which should be 0. And go ahead and click on this Ethereum mainnet. We're going to switch our network to the Kovan network, which is what we'll be testing on. So once you click that dropdown, you should see Kovan test network. And so go ahead and click on that. As now you can see, I actually already have some Kovan ETH, but you're probably going to need to get some. So the way to do that is to go to a Kovan testnet faucet. So let's go ahead and do that now. So there are two main faucets for Kovan. I'll make sure to link both of them in the description below. The first is this skitter.im. Basically, there are some instructions here, but you have to sign in, make an account, and then post your address, and then you'll be able to get some Kovan. The other is this faucet.kovan.network, where you can log in with GitHub and request Kovan. If you really get stuck on this, go ahead and drop your testnet address in the comments or DM me, and I might be able to send you some. The next step is to get some Kovan testnet link, which is we're going to be using. It's a fee that's paid to get our verified random. You can do that at kovan.chain.link. Go ahead and paste your address and then send yourself some link. One thing to note is that testnet link needs to be added as a custom token on Metamask. So you see I have 0 link and 125 testnet link. So this testnet link is the actual link, and you have to add that by doing this add token. And then you go to custom token, and you put in the token address. I'll link that in the description below, but you could always Google on Chainlink stocks, and they have the testnet address there. So in order to code a contract that's using Chainlink, you need to use the Chainlink starter template, which has all the built-in dependencies that Chainlink is using. So on the Chainlink docs, if you go to docs, chain.link/docs/get a random number, I'll link this in the description. You have this VRF consumer base contract. So if you click on that, or if you go and click down here on this deploy contract using Remix, we can open up their test VRF contract. And VRF is just their randomness product. So here we are in Remix. That link automatically opened up the Chainlink here. So just a quick tour of Remix. These are our files. This is our compiler. This is where we're actually going to deploy the contract. And then here are extensions if we actually need them. But for now, let's look at the files. You should see something in here from Chainlink. So to click on that, you'll see random number consumer.sol. This is a Solidity file with that extension. So that's what all Ethereum smart contracts are coded in. Actually, not all of them. There's another language called Viper, but Solidity is the most popular one. So if you click on that, you can scroll through the code here. You can actually see this is the link token address I talked about earlier. And this is the starter template for code that uses randomness. Basically, there's the constructor, which in Python, you might be familiar with an init function for a class, for an instance of a class. So this is basically just the code that runs at the exact moment that the contract is deployed. There's also a getRandomNumber function, which requests the randomness from Chainlink, and it uses a call and response kind of format. So this getRandomNumber will actually call the Chainlink in order to get a random number, and then when the Chainlink node or the Oracle node, which is providing the randomness, fulfills the randomness, they will call a function on your contract, right? So it's happening asynchronously, where first you're sending out a message to request the randomness, and then you have this special function on your contract that they can actually call and populate that randomness. So if you go ahead and hit save, or like Control S or Command S on Mac, you'll see that there's artifacts, which is basically some of the things that the imports and stuff. But if you go over to deploy, you'll see, or the compile, you can see that we can actually compile this contract. I like to have auto compile selected. Just as you're working, it'll automatically compile. So we have our contract compiled. Now we can go to this deploy feature. Normally in Remix, if you're deploying your own smart contract that you built from scratch, you can deploy to locally using the JavaScript VM. But because we're using Chainlink and we're using the Kovan Chainlink testnet, we need to deploy on the Kovan network. So in order to do that, go ahead and select Injected Web3, which means that Metamask is going to be handling these transactions. And then you may need to actually approve. You might get a pop-up from Metamask, and you might need to approve the connection to Remix. Once you do that, you can actually deploy the contract. So go ahead and hit deploy. And here we are. We have to approve the deployment for Metamask. This is where our ETH comes in, our Kovan ETH. We have to pay gas to deploy. And so that takes ETH. And so we go ahead and confirm that. It will be subtracted from our ETH balance on our Metamask account. But because this is testnet ETH, it's not actually worth anything. So there's no problem there. So once we deployed, we can see in our deploy contracts, we actually have our random number. And so what we can do is we can get a random number, and then we can look at the random result. So this random result is a public variable, which means that anyone can actually query it and see what that is. And you can see our fulfill randomness is setting the result that Chainlink fulfills, right? So the Chainlink is calling this function, remember, with randomness as a parameter. And so that parameter is being placed in this random result. So if we click random result now, so the random result is 0 right now, but we can go ahead and use this function to get a new random number, which will be stored on this random result variable. And so in order to do that, we need to input a random seed, which actually is not used by Chainlink anywhere in the code, but it is a legacy thing that you just kind of have to do to call. So, so we can put a random seed and let's see what happens. Oops, we have this gas estimation failed error. So the reason this is happening is because this contract doesn't have any link to pay the Chainlink node that's providing the random seed. That's what the Chainlink tokens are actually used for, to pay Chainlink nodes. You can see they have this big comment, stop, this function will fail if this contract is not on link. So we need to go ahead and add link. So we have the actual address of the contract. We can copy that here. And then I'm gonna go ahead and open up my MetaMask. And you see I've added this as a custom token. I've added the link token, which the address is in the docs. And so I can do that, and I can send tokens to my address. So let's just go ahead and let's just send to link. And then we're gonna have to approve that. Okay, so that's pending. So that will take just a little bit of time to run. So we'll be right back. Okay, we're back. That should have had time to run now. And so now we can try running this get random number contract. So we're popped over to Metamask to approve the transaction. We just have to pay the gas with our Kovan ETH. And just like that, the transaction was sent. So you can actually click on the Etherscan link in order to see the transaction. And here's the response. And so we can actually click on random result again, and we should see a number that's a new random number. Again, it takes a minute to actually call the function, right? So now the request is going out to the Chainlink Oracle, which is hitting a Chainlink node, sending that back to the Oracle, which is sending it back to us. Okay, so I just hit that random result again. So it takes a minute to update, but you can see we have an int that's random. So now we can go ahead and jump into the code to turn this random number that we're getting into a spin on a roulette wheel. Okay, so here is our roulette wheel contract, just a little diagram so we can see how things are working. The contract is denoted by this roulette wheel. And so we basically have a few interactions. In order for a casino to run, they need to have a reserve in order to pay out winning bets, right? And this reserve has to be big enough to cover any winning bets for the user and losses for the casino that might occur. And even though the casino has an edge, they need to cover a stream of what you might consider bad luck. And so we have basically three different interactions taking place. The first is this connection to Chainlink with our smart contract. And so that is actually what we've already done with the getRandomNumber function. So we use Chainlink to get a verified random number in order for the roulette spin. The second is a user actually spinning roulette. So this is going to be a function where they can send ETH as value and place a bet using that ETH. And then if they correctly guess the right number, so they'll send ETH and a number, and if they correctly guess it, then we'll send them back their winnings. The third interaction is with us, denoted by this user here, or the owner of the contract. And we can basically put money into the reserves of the contract so that they can pay out the correct amount to people and never be short. And we can also receive money if we want to, withdraw it from the reserves. That part is optional. What you could do is you could have a contract that just is completely self-sustaining, that no one's profiting off of, or you could even change it so that it distributes these to people who own certain tokens. Maybe you create a casino token that earns a share of revenue. But for this example, we're going to actually just be able to withdraw it into our account. So the first thing that we need to work on is this constructor function here. So this is the function that actually runs when the contract is deployed. And the main thing we need to add is our ability to control certain functions of the contract. In order to do that, we can store our address that we're deploying from. In this case, it's whatever your MetaMask address is, as kind of an administrator of the contract. I like to think of it as the casino because they're the ones actually managing, this gambling thing. So we can write casino equals message.sender, which means whoever sends this constructor function call, which is whoever deploys the contract, is actually the one who will be this casino. So we want to be able to pay the casino, aka us, from the reserves in the contract and vice versa. In order to do that, we need to make this a payable address. And in Solidity, you need to declare your variables and their type before you create them, and unlike Python or other languages like that. So we need to go ahead and declare it. And so this is just going to be an address payable casino. And so in this case, we want to be transparent. So I think I actually want to make this public because making it public will allow people to know who's actually controlling this thing. And it looks like I spelled address wrong. So that should fix that error. Cool. So now we're going to create a function to actually add balance to the contract. And so that's going to be a pretty simple function. And you could actually get around this by just sending ETH directly to the contract. But if we're working in some kind of deployment environment, like I said, this is unnecessary, but it's just something that I did when I first made this, and it's kind of good to understand how it works. So we can add function, add balance, which is adding balance to this contract. It's an external function, which means it can be called externally, and it's payable. And it's actually an empty function. So all this means is that someone can just add balance directly to the contract. It doesn't do anything except accepting that balance. So this payable means that people can send value in ETH along with calling the function. If we wanted to, in the future, we could also return the current balance of the function, something like that. So if we're depositing money, we want to be able to withdraw it as well, especially for testing purposes. So our next function, we're going to say function withdraw away. Way is the smallest unit of Ethereum. And in smart contracts, when you deal with ETH, you're actually dealing in units of way, which is the very smallest unit. So this is going to accept uint. We can just make this way amount, or even withdraw amount, withdraw way amount, just to be very explicit. And so this is going to be a public function. And so what do we want to be able to do with this function? We want to be able to transfer balance from the contract balance to the casino balance. We have that casino address up here and up here, and that's going to be our address for now. And so we can go ahead and do casino.transfer. This is possible because it's a payable type, address type. So we can do casino.transfer, and then we can do that withdraw away amount. And yeah, so now we'll be able to withdraw and deposit into this smart contract. So now let's go ahead and start building the actual function to spin a roulette wheel. So I'm going to go ahead and create a new function up here. It's going to be very similar to this getRandomNumber function, but for now we can just leave that getRandomNumber function and create this function. So we can do function. I'm going to call it spin wheel because that's what the user is doing. And this is going to be a user-facing function. This is the function that a user will interact with in order to spin the roulette wheel and make a bet. So just like the getRandomNumber function, the user will need to provide a seed. So we can copy in that variable that's being accepted. So in addition to the seed, we need to add an actual number that the user can use to place their bet. So a roulette wheel traditionally is numbered 0 to 36, depending on the roulette wheel. And so they should be able to place their bet on one of those numbers. And so we're going to create another uint, and then we can just call it betNum. So this is the number. So if they want to bet on lucky number 11, then they can just go ahead and use this variable here in the function call in order to place that bet. So like we said before, this function needs to be payable because they're sending value along with the function call in order to make a bet. So that value that they're sending will be their bet amount. So I'll make it payable. And of course, it's a public function because users are going to be able to interact with it. So first things first, we want to know who's actually sending this. So we're going to record that. So we can do address type. It's a payable address because we might have to pay them if their bet is a winning bet. And in this case, let's just call them the bettor. So they're the bettor, and we just want them to be equal to whoever calls this function. So we can say equal to message.sender. Okay, so now we need to actually request the randomness, just like in this getRandomNumber. And we can basically just copy these things in order to request randomness. Okay, so also let's just put a comment in here. So comments in Solidity use a double backslash, just so things are easy to remember in the future. And now we actually have to request randomness from Chainlink. So we can actually call this getRandomNumber function. This is going to be bytes 32, which is going to be the job hash. And then we can say current request or something is equal to getRandomNumber. And then we need to put in the user provided seed. So it's important to remember that this current request, this is the ID. So here we can put current request ID. This is the ID of this request. It's not actually the randomness, because the randomness will be fulfilled coming from this fulfill randomness function when this is called. So the Chainlink Oracle is actually going to call this fulfill randomness function in order to give our contract back the randomness. In order to know from which spin that randomness was coming, we need to actually record the job ID, right? Because this person is going to spin. Maybe someone else will also spin the wheel before we get our randomness back from the first spin. In that case, we need to know which belongs to which. So that's what we're going to do now. And so the first step is to record that request ID so that when this job comes in, the request ID is actually given to us. Like, hey, this was a request that you made at this time, and here's the random number associated with that request. So how are we going to know later on what the bet was and who sent it and what the request ID was? Basically, we need to store all of these into a new Solidity type called a struct. So let's go up to the top of our function where we can declare a new variable. So I'm going to just copy and paste this code here. And so this struct, let's call it a bet. So a bet, right? The record that we're going to have of one bet is going to include the address, the bet number. So that's the number that they're placing the bet on, lucky number 8, whatever your lucky number is, and the amount of the bet, right? And so these structs are basically lets you store. It's a data type in Solidity that lets you kind of choose the structure that you want to store. So we know that every one of these is going to have an address, a bet number, and an amount. So now we can go ahead and populate this, and then it becomes easier to access later on. Now that we have that data type, we actually can create a mapping. In other languages, it might be called a dictionary or a hash table, but we basically want a library of these bet data types, because every time someone makes a bet, we want to be able to kind of look into that library and then see what the bet is, or record it and then see what it is when we're ready to pay them out when we get the randomness. So we can create what's called a mapping. So let's go ahead and paste that in here. So this mapping is of type from type bytes 32, which is the key value, to a bet. So for every byte 32 key, there's a bet kind of as the value associated with that. And so if you remember, our bytes 32 is the format of our job ID. So if we go back down here, we have this bytes 32, the current request ID. So that ID is going to be what we can use to access the bet. And I went ahead and made this public just because it's not a bad thing to be able to access. I haven't really thought through exactly what I'm making public and what not, but this is just kind of a demo contract. So you can make your own decisions as far as that goes. So now that we have that data type, the bet data type, and the mapping, we can go ahead and store this current bet into our book so that we know in the future when we receive the randomness who we can pay. So let's go ahead and do that. Okay, so I went ahead and copied this in. And so this has the current bet. Right now we're storing it in memory. And like we said before with the data type that we just structured, we have the better, the bet number, and the value of the bet. And so we're storing all of that using the key, which is this current request ID from here. And we're saying that equal to that bet data type, which is what we're storing, all from this transaction. So now anytime we want to access the bet number, who it was from, and how much they bet, we can just pull it right out of this book. Okay, so now that we're accepting payment and the bet number, and recording all of that information for a bet and then requesting randomness. Let's see what happens when we actually receive the randomness, because this is where we'll be putting the logic to pay back the bet if it's a winner. So when the Chainlink Oracle calls this function, they'll be giving us our randomness, which we're storing in random result. And they're also sending the request ID. So the first thing that we need to do is pull our bet out of the bet book from our request ID. Okay, so I've pasted this code in, and as you can see, we're loading this bet from memory out of this book that we created earlier, which is our dictionary. We're using the request ID, which is this input here, as the key to get our values, which is the bet. And then we're populating those values into these variables. So that includes the bet number, the bettor, and the amount. So the next result is to actually figure out what the result of the spin is. So as you can see, this uint that the random number, the random result is returned as, is really long and doesn't really have anything to do with a roulette wheel. So we can pretty simply convert this number into a number within our range of numbers for the roulette wheel by just using a modulo. So I've gone ahead and done this spin result variable, which is an int, is equal to the random result, which is what we're getting from this function call, modulo 30, and we can make it 36 for our roulette wheel. So one thing that we can do is record this result, kind of like this random result. We can record a spin result. So here, it only works if it's a low volume, because if there are multiple people doing this before we get that response from Chainlink, then they won't be able to see their spin result, and the spin result will constantly be changing based on the newest randomness received. That said, it's useful for testing, and so we'll go ahead and if we make a variable here, remember we have to declare it, and so we're going to declare that outside of the function as a public variable. Okay, so I've declared that publicly. Here's the spin result, which means that we'll also be able to call the spin result when we want to. Okay, so the final step and the most fun step for our users is the part where we actually pay them if they're a winner. So the way we can do that is by seeing if their number matches a number. So in roulette wheels, normally there is one or sometimes two numbers that are the zero numbers or double zero, and that's what gives the house its advantage. So in this case, we're actually allowing our users to pick one out of 36 numbers, and then we'll be paying back 35 times the money if they are correct. And so that builds in a little bit of a house advantage. And the reason that's important is because it allows our reserves as a casino to grow, which means that we can start taking bigger and bigger bet sizes. Okay, so here we have our little snippet of code that's actually sending the value. So we're checking if the spin result is equal to the bet number. So this is the number that our user bet, which remember we're getting from our book through this bet struct. So you can send value to the bettor using this call method. And so we're basically calling the bettor's address, and we're attaching to it a value, which is the amount that they bet times 35 with our house advantage baked in. And we're requiring that we basically get a positive result back from this. So if for some reason the transaction fails, then this would fail. So that's the basic structure and frame of our contract, but there are a few edge cases that we should probably handle. The first is, what happens if someone places a bet that we don't have the funds to pay out? Well, one way that we can avoid that from happening is by setting a maximum bet size. So let's go ahead and do that now. So up top here, let's go ahead and set another uint, and let's say it's the max bet, and let's say that's equal to 1 Ether. And Ethereum actually lets you use Ether as a unit. So we're just setting this as a default value, but it can change as people interact with our contract and as our reserves change. So let's go ahead and look at some moments where we might want to change that. Okay, so here we are at our spin wheel function, and there's actually a way that we can use another feature in Solidity to handle our checking the max bet, because when someone spins a wheel, we want to actually check and make sure that their max bet is below our max bet that we're setting. So we can create what's called a modifier. A modifier is basically something that you can use to modify a function. In this case, we are creating a modifier that requires that the value of the message that's calling the function is less than or equal to the max bet. So before the function even starts to execute, it will check that the value attached is less than the current max bet value that's set on the contract. Adding a modifier to a function is pretty easy. We can just go right in here to our spin wheel function where we want to add this modifier, and then just place this check max bet before the function code. And so now that modifier is attached to this function. Now we'll need to go ahead and change our max bet amount as things happen within our function. So if we withdraw away, we want to change the max bet. So what we can do is we can actually add basically a little bit of code to update the max bet based on our current reserves in the contract. Usually what we want to do is have a fraction of reserves be the max bet size. And so we can actually go ahead and create a variable that is another uint. So we're choosing a max bet ratio of 1000. This may seem like a pretty high ratio, but if the contract gets unlucky and people just win a few spins in a row, you don't want to lose all of your reserves. Now we need to go ahead and dynamically update the max bet using this ratio. So under this withdraw away function, we can add just a little snippet of code that will check the current balance. This address of this is checking the smart contract roulette wheel smart contract balance, getting that balance, and then dividing it by the max bet ratio. So whenever the balance changes, we can do the same thing up here in this add balance. So what this is doing is whenever the balance is changing, we're basically updating the ratio. When else would the balance change? Well, when we make a payout and someone makes a bet. So when someone makes a payout, so we pay them here, so that means we're losing money in our contract, and we can go ahead and add this to update the max bet based on the current balance. One of the final things that we can do is if we actually successfully pay or process a bet, then we can delete it out of our bet book because it's no longer a pending bet. So here we can go ahead and delete that. So Solidity has a delete method, so we can basically delete a specific item inside of one of the mappings. In this case, that's going to be the current request ID. Well, there you have it. That's our smart contract. Now it's time to go ahead and deploy and test the smart contract. Obviously, this is just an example. And so if you actually want to deploy this in real life, you would want to audit the contract. And there are a few things that you might want to change. But for now, let's just see how to deploy it. So before we deploy, I actually want to change the name of this contract. So you can do that over here just by right-clicking, and then you can rename. And so we can just call it Chainlink Roulette. So one thing that I didn't check before is the contract actually has a name within the contract code, not just a file. So we want to change this as well to Chainlink Roulette. And then we need to recompile. Okay, so that's compiled. And so now we need to redeploy. So this is our old contract. You can see it has the old name, random number contract. So go ahead and deploy. Make sure that you're using injected Web3, and it shows us that we're on the Kovan network on our Metamask. We confirm, and now we wait for the deployment. Just for fun, we can go ahead and look at that Etherscan. And you can see that the address is my test address I made from Metamask. Okay, so that went ahead and confirmed. And so our contract is deployed. You can see it here in the sidebar with our random number contract above that. I'm going to go ahead and X that out just because we don't need to access that anymore. That's our previous saved version. And so here's our Chainlink contract, and now we can actually interact with it and test it. The first thing we can do is check and see some of our public variables. We have our max bet ratio, we have our casino. So this is actually my test address. And yeah, so remember, one thing that we have to do is send link to this contract. So I'm going to go ahead and do that in my Metamask, and I already showed you how to do that before. So I'll jump back when it's done. So unlike before, one thing that we need to do now is actually send ETH, testnet ETH, in order for our contract to be able to function and accept bets. So we can use the add balance function to do that. So in order to attach value to a message, you can actually go up here and there's a value section in Remix, and you can choose your unit. And so in order to calculate units, there's a tool you can use. Sometimes it's hard to remember all the decimal places because there are so many. And so we can say like 1 ether, we can see it's equal to this many, Gwei, gigawei, and actual way. So in this case, I want to send 0.1 ether. And so I can see how much of each of these I need to send. And actually, let's say 0.05. Actually, we'll say 0.1. I can copy this value, go ahead and paste that into this value of way that I'm sending. As you can see, it's a lot of zeros. And then we can go ahead and hit add balance to this contract, which is our balance function that we would call. And so now this balance is what's being sent. So I've confirmed that on Metamask. So our contract should have the balance. Now we can actually do the fun part and spin the wheel. So here we need to, again, provide some balance. So I'm going to go ahead and take a bet that is, we'll go ahead and do 5, and then we're going to take off a few zeros, 1, 2, 3, 4 zeros from the balance that we actually added to our contract, because we want to be within our limit of 1/1000th of our total reserves. So now I can interact with this contract through Remix by adding our user-provided seed, which can be any random number, and then our actual bet number. So to me, 8 is a lucky number, as it is to many people. And so I'm going to go ahead and hit 8 and hit transact. Obviously, we have to confirm with our Metamask and see in ETH what that is. So we'll go ahead and send that. And so now we can go ahead and look at our random result. Right now it's 0, but this should take a minute to update from our new Chainlink value that we actually received from the Chainlink VRF. Okay, it's been a minute, so let's go ahead and see if our random result has updated. Okay, our random result updated, so that means our spin result should be a number between 0 and 36. And it's 27, so unfortunately our bet of 8, it didn't work out, but the wheel successfully worked. So that's everything you need to build a roulette wheel using Chainlink VRF and actually deploy it. If you want to deploy this on mainnet, you could do that just by, instead of having Kovan selected in your MetaMask, have mainnet selected. If you found this video helpful, please leave a like and subscribe because it really helps out the channel. If you have any questions or suggestions for my next videos, please go ahead and leave comments down below and I'll try my best to get back to you. Thanks for watching and I'll see you in the next video.